Presentation is by Charles Byrne, speaking on the shape and history of the moon. And what we'll do is we'll start waving at you after 10 minutes. After 12 minutes, we'll stand up and be a little more persuasive. Okay, Charles.
We're going to be talking about modeling the moon, the whole moon, the topography part of it, and imply some subsurface work. The moon, of course, is dichotic in many ways, from the maria, the bulge on the far side, thin crust on the near side, etc. And so that's a problem for a modeler. It's got to find something that's dichotic. The near and in general, that's the near side and the far side of the moon. The near side, our familiar man in the moon maria. Far side, very little maria, very rough. This maps of the current moon have captured 17 orbital spacecraft, if I counted correctly, and about a dozen landings, some hard, some soft. And we're going to be talking about topography and particularly the digital elevation map of a moon, of the entire moon, such as this. This is Kagaya, 1 degree. The vertical scale is mine, starting from white and going through the spectrum and down to black. The display is simply a graph of latitude and longitude, a lot of distortion at the poles. So that's our base map. Now, of course, the moon is 95% at least shaped by impact, and we're going to expect the dichotic shape to be impact as well. This is the Maxwell Z model of hypervelocity impacts, and it's been extended by many post-Maxwell people, such as Croft and Malash and Ivanov and Richardson, and I've put 2 extensions on here that I'll talk briefly about. The difficulty that has been always placed on using the Maxwell for large features is that for small features, the Maxwell Z simple model says depth diameter will be a constant, and so it is. But at the moon, anything over 10 kilometers in diameter, that's an impact, is progressively shallow. And so in order to use the model for that large area, you have to scale separately by depth and diameter. Then, when you do that, these are the radial averaged elevation profiles over azimuth of a few impact features from, here's the central peak of Tycho, all the way up to the double rings of Oriental. Using that self-scaled model, that self-similar model, here are all the impact features that I could find, starting, of course, with the Don Wilhelm's list, that are 200 kilometers in diameter or larger. So these are large craters plus basins. And as we can see, and as Zuber and Williams showed, they cannot form the dichotic shape of the moon. There's not enough of them. The SBA South Pole Aiken Basin is not shown here, but it isn't big enough either to do that job. It helps. So we're going to look for the big guys. What impact features could form the dichotomy? And I'm going to look for megabasins. A megabasin, a basin that contains other basins. There's several uses of that. And the thing that's different about a megabasin is that the ejecta pattern, the trajectory is no longer the old cannon ballistics. So you need the velocity profile of the ejecta when it's launched. And this is the far field, the intermediate inertia field that Richardson wrote about. And at the end, I've tailored a velocity drop-off that forms the rim and fits that self-similar model. Now, the search for megabasins that would explain the dichotomy was done by writing a program that simulates using these scaled model and 2 megabasins, the South Polagan Basin and a mystery basin. Then changing the parameters until we got a best fit to the topography. The result is this picture, 3 megabasins. The South Polagan Basin is now in here. This is a near side megabasin, and it is big. Its radius is 110 degrees. So you can't see it. You can see part of it. In fact, the whole near side and all the landing missions we've ever done are in this flat floor. The flat floor is crustal, and that's what all megabasins have. It's the melt column that the simulations have, in the last couple of years, have been showing. This little one over here is a small megabasin that you just need in order to finish modeling the topography. I call it St. John Chelius. Its western rim cuts through Moscoviennes and complicates that feature quite a bit. Okay, now we put the impact features together, and both the megabasins and the smaller ones, and now it starts to look a little bit like the topography of the moon. We've added the Mara here, the fill that goes into the impact features, and we subtract that from the topography to see how good we're doing. How are we doing it? Okay? Well, the answer is we're not doing too badly, but we've got this big depression in here in the Mare Orientale region. We've got some mounds here, there, and the other place. So let's go model these, and we're going to use simple cosine squared models for the mounds, but we've got to do a special array of cosines for here, and it looks like this. Let's talk about this depression first. This depression here is under Nubium, Orientale, and Fregoris. I'm going to propose, everybody can play the game, that there was a melt pool of lava under the crust here, and that the flows into Imbrium, Orientalis, have depleted that, allowing the crust to sink into that depleted area, just like pumping oil out of Long Beach, since we're in California. The land sinks and the crust sinks. And that has left this depression, which is modeled by a series of cosines and whose axis is aligned with the axis of the near side megabasin, the major axis, because it's slightly elliptical. And so I think the cause of this is an impact, near side megabasin, that has stirred up the incompatible layer and upper mantle and been the source of that lava. Put them all together, we have the comprehensive model. And that shows the comprehensive model compared with the topography. That was what I showed on my title slide. So out of one impact model that works for small and large hypervelocity impacts, plus about 6 ad hoc models, which I believe the mounds, I didn't talk about the mounds, but I believe the mound, like the Central Highland here, impacted by Nectaris and Sinus asperitatis, are returns of material that was ejected to escape by the megabasins. And they've caused subsonic impacts. And I think this was before Nectaris. Nectaris took a bite, just like SPA took a bite out of the far side mound, which was caused by the ejecta from the near side megabasin. Now here we have the explanation of this topography and the far side mound, et cetera, et cetera. Look at the detail that comes from this single thing. I'm going to use 1 minute to talk a little bit about the near side megabasin. This is a Lambert equal area display, 150-degree range, so you're looking around the moon a bit. Here, the center coordinates are 24 degrees east and 10 degrees north. And if we'd had that display after Clementine gave us the data, then I wouldn't be talking today about the near side megabasin. We would have seen it long, long ago. This is a radial profile showing the model matching the radial profile of the moon. This is the flat floor, the rise, the rim, the slope up to the peak of the far side bulge. I've removed a model of the SPA in order to get this match, and it is a remarkable match. That's all I've done, to remove that same model that I've been talking about. I will just mention that the flat floors are due to the impact dynamics of megabasins. This is Sarah Stewart's still shots from her movie that you can get on her webpage of an oblique impact at the SPA, and it shows the penetration to the mantle, the rebound of the mantle, and finally the mantle forming a thinned floor. Okay, and now I promised the history of the moon. 2 years ago, I gave a talk using zircon crystal data from Australia, Neptune and Pigeon, at 4.34 billion years ago for the near side megabasin. I'm not sure of the sequence of those three basins, and I'm going to, in less than a minute, go through the history of the moon, the megabasins, the pre-Nectarian, the Nectarian, the Upper Imbrium, the addition of the Maria, Eratosthenian, and the Copernican, which gets back to our comprehensive model. And I'll cut the summary and ask for questions.
Time for a few questions?
Yes.
Have you integrated any of the LOLA data so far into your model and your results?
Not likely, not yet. And I expect at the 1 degree resolution, the LOLA data should be, maybe somebody's done that, should be identical to the Kagaya. But also I used the 1/16th degree Kagaya to get the model of the individual small impact features. So I'll be looking forward to anybody that compares those two and to talk about them. But at 1 degree, I can't see a difference. Okay.
Next presentation is geologic analysis